Welcome to this short lecture course on complex functions at the University of Oxford. My name is Pedro Ferreira and I'll be your guide to this wonderful topic. You can access my website at pedroferreira.co.uk and find my lecture notes in the teaching section. I'll follow them very closely, but there are also many books you can use in parallel. Here are a few and they're listed in my notes, as well as many lecture courses online. I'd like to warn you that there are mistakes and I'm constantly updating the notes. If you find mistakes, email me at pedro.ferreira@physics.ox.ac.uk. Okay, let's begin. By now you've learnt what seem like two very different topics. On the one hand, you have complex numbers. On the other hand, you have this whole baggage associated with vectors. You've got vectors, you've got linear algebra, you've got vector calculus, you've got multiple integrals, you've got all this wonderful stuff. Now, you might have guessed that there is a connection. In these lectures, I'm going to show you that there is, and more. I'm going to show you that this connection is quite deep and that complex functions and everything associated with complex analysis is magical and lets you do unexpected things, in maths, of course. But to do so, I'm going to start off very basically remembering some of the stuff you've learned. And I'm going to begin by talking about two-dimensional vectors. Suppose I have a two-dimensional vector with coordinates x and y. Now, we know that we can add two vectors. So suppose we're given a vector x1, y1, and we add it to a vector x2, y2, and we know how to do that. We add each of the components and we get something like that. Well, what if you were asked to multiply them? You've done dot products and cross products and things like that, but I just want a multiplication that takes you from two vectors to one vector. How would you do that? Well, I'm going to make it up. I'm going to get vector x1, y1. This dot is just my made up multiplication sign, not to be confused with the dot product. And so I've got x1, y1, and I'm multiplying by x2, y2, and I'm going to define this multiplication. In the x-axis, you combine the x's and y's in this way, and in the y-axis, you combine them in this way. Okay? It looks odd, it looks a bit familiar, but let's just see if we can try and build up towards something we're really familiar with. Suppose we write down our vector in the following way. It's a two-dimensional vector. So I can define a basis, E1 and E2. I won't say the hats, but hats are always implied. And I'm going to define this multiplication in terms of E1 and E2. In other words, if I multiply an E1 with an E1, I get an E1. If I multiply an E1 with an E2, I get an E2. If I multiply an E2 with an E1, I get an E2, and if I multiply an E1 with an E1, I get, an E2 with an E2, I get a minus E1. Okay? We'll see that if you plug those E's up into the expression that I have up here, and I follow through and do this multiplication here, I'll get exactly the right answer. Let's just change notation a little bit. Let's just say that E1, I'm going to represent it as the number 1, and E2 as the letter I. Okay? Well, then I have that my complex number, which I could write in this way, my vector I could write in this way, is really something like that, where I've suppressed the 1 here for obvious reasons. And so you can see that all along we could have been talking about complex numbers. And this multiplication up here, which I've underlined, I'm underlining again, is nothing more than the multiplication of two complex numbers. This means that we can think of a complex number, and this is not new, this is something you've known all along. You can think of a complex number living on a plane like that, and this plane is known as the Argand plane. Okay? We can complicate things just a little bit by including infinity in the Argand plane, in some sense closing it off. And a good way of thinking about it is to plonk the unit sphere on this plane such that the south pole is on point 0, 0, 0, and the north pole is at 0, 0, 2. And then we take any point on the sphere and consider a line that intersects the north pole, that point, and then extrapolate it so that it intersects the xy plane at p hat. Now think about that. That means that all points on the sphere are uniquely mapped onto the plane, while the north pole is a special point because the line has to intersect the north pole and intersects the north pole, and will go out and intersect at infinity. But all points at infinity, anywhere in any direction, will be mapped onto the north pole. In other words, that sphere you can think of as encapsulating the Argon plane plus infinity in all directions. That sphere is known as the Riemann sphere, and this projection is known as the stereographic projection. And it's useful to write it out. So if xy are your points on the Argon plane, your points on the sphere are 2x over 2 minus z, 2y over 2 minus z. And now suppose you have your points on the Argon plane and you want to project them onto the sphere. That's a z there, I'm sorry. Well, the mapping is just a little bit more complicated, but it's just the inverse mapping. And it's 4x over 4 plus x squared plus y squared. And 4y, 4 plus x squared plus y squared. And then 1 plus minus 4 plus x squared plus y squared. 4 plus x squared plus y squared. And that's the complete mapping. All right. Now, there are a number of things you can do if you remember that it's this complex number lives on the Argon plane. Let me just draw the Argon plane again, and very conveniently it makes these lines straight, and I have this complex number here, z. And first thing you can do is imagine that you reflect this number across the x-axis. So you bring it down here, okay? Well, when you do that, something very interesting happens. Basically, when you reflect across the x-axis, what happens? Your y goes to minus y. In other words, we have an operation that creates a new number, a new complex number. Let me call it z bar, and it's x minus iy. And this is quite a special operation because you can't really get it from the conventional operations you know. In other words, you have that this z bar is not simply the multiplication of z by some other complex number. It's a completely different operation. In other words, z bar is linearly independent from z. It's completely independent. Now, once you have this complex conjugate, and let me write that down, there are a number of things that you can do. For example, you can work out the length of this vector. And let me put a little arrow there. And the length of the vector is modulus of x. Z squared is simply z times z bar, which is x squared plus y squared. And for convenience, I'm going to call that r squared. Okay. And if you define the length of that vector, you can also define an angle. Let me call it theta. And we call that the argument of z is theta. And this means that we can represent a complex number as re to the I theta. Okay? And this is quite useful. Note that over here I'm using something called the Euler's formula, which I can write down here. And this is just to remind you, you should know all this stuff. Now, there's an interesting thing to note here. I wrote that argument of z is theta, but I could really have added any multiple of 2 pi and I would still have got the same answer. I mean, if you look at Euler's formula, if I add theta 2 pi to theta here and 2 pi to theta here, I'll get back exactly the same complex number. So we already see something interesting. In fact, the argument of a complex number is multi-valued, where n belongs to the integers. Now, we could pick, as I said, we could pick any value of n and we would get the same thing. Let's use Euler's formula and the multi-valuedness to remind us of two interesting results. Okay, so I wrote down that we could write a complex number in this form, and due to multi-valuedness, really I should write it down in this way, where n is any integer. Okay, and the first thing, let's remind ourselves of an incredibly useful formula. And if you remember, you have that if you take z to some power, you can use de Moivre's formula to write it out in the following way. And note that it's not some hideous mess, some nth order polynomial in cosines and sines. It just becomes very simple. And this is all due to the fact that we can write z as r to the e I theta. But the other useful thing is if we want to look at roots. In other words, suppose we work out what z to the nth root of z is. It's going to be r, that we do that to the modulus, and then we have that the angles arrange themselves in the following way. In other words, where k is an integer that goes from 0 to n minus 1. In other words, we get n roots, but not only that, these n roots lie on a circle, but are neatly laid out on a circle, equidistant from each other, well, adjacently equidistant, to form a polygon with n vertices. So that's quite useful, and it all comes from this notation, this fact that you can write it as r to the ei theta and that it's multi-valued. We've been talking about numbers, but what we're really interested in is functions. And so really we're interested in functions which take x and y and map it onto something. Now, the simplest thing we can do is map x and y onto some real number, and we've done this a lot in the past. We map it onto it, we work out surfaces, and there are all these things we can do. But what we're really interested in this lecture course are functions that take x and y and map them onto another pair. So functions that map the Argand plane onto the Argand plane. In other words, each one of these u and v are functions of x and y, are real functions of x and y. Well, the best thing is just to look at some examples. Let's look at some simple examples. Let's look at this one first. This one is super simple. Let's take x and y and output that. Let's get another one which is in some sense even simpler. We take x and y and we map it onto the real line in the following way. And in that spirit, again, let's take x and y and map it onto the real line, but in a slightly different way. All of these are legitimate functions of x and y, and they map the plane onto the plane. Now, the focus of this lecture course is going to be functions of the complex plane. So the first thing we want to do is, can we re-express these functions, instead of being of x and y, as functions of z and z bar? So let's just recall that we have that z is x plus iy, and z bar is x minus iy, which means that we can invert this relationship and express x and y in the following way. Okay? Well, if we do that, we can go away and try and re-express these as functions of z and z bar. And what do we get? Well, we get that f maps z and z bar onto z squared. This one, f2, maps z and z bar onto z times z bar. And this one is a god-awful mess, and I will write it out for you to see what it is. Z cubed plus 3z squared z bar plus 3z z bar squared plus z bar cubed plus, and we can't forget the complex part, z squared minus z bar squared. So these functions look pretty simple on the left-hand side when you do it in x and y, and some of them look even simpler when you do them in terms of z and z bar, but f3 looks absolutely horrendous. Now, what we are going to do in this lecture course is we will focus on functions of z alone. Okay? This means that they do not depend on z bar. Another way of putting this is that we're going to concentrate on functions which are independent of z bar. Okay? So let's consider some examples. The simplest example is the function that maps xy onto xy. Now that is nothing more than f of z equals z. And we can make it more complicated. We can take powers. In other words, we can have f of z equals to z to the n, where n is any positive or negative integer. And if we can do powers, we can do series expansions. So we can construct a lot of the elementary functions you're used to. So for example, we can have f of z is nothing more than k equals 0 to infinity z to the k over k factorial. And what's that? E to the z. And we can do f of z equals k equals 0 to infinity minus 1 to the k z to the 2k over 2k factorial. And what's that? Cosine of z. You can see where I'm going with this. Let's just do one more for completeness. And minus 1 to the k z to the 2k plus 1 over 2k plus 1 factorial. That's sine of z. All of these are legitimate functions of z. Okay? But there are some functions which have interesting properties. So for example, if we consider the following functions, and we'll see that they're multi-valued. So for example, we've seen that the following case, f of z equals the nth root of z, where n is some positive integer. That's multi-valued. We've done that already. Another interesting one and quite useful one is if we look at the logarithm of z, right? And so let's just write this as logarithm of z, and if we expand that, that's going to be logarithm of the modulus of z plus I times the argument of z, and that is nothing more than ln r plus I theta plus 2 pi k, with k in the positive and negative integers. So it's multi-valued. One final point I want to make is there are some functions that look simple but aren't functions of z alone. So some functions are simple, but And let's consider the example that we had above, which was, I believe, f2. That's z, z bar. There is no way we could write that as a function of z alone. But it looks very simple. But we can't be deluded. This is not a function of z.